Hello, everyone. This is Professor DePaulo. Welcome you back to Psych 220 Behavioral Statistics Review of the Labs in SPSS. And so this lesson is going to be on SPSS Lab 4 Intro to Hypothesis Testing and the Sign Test. So this is a launching point of hypothesis testing using the binomial as the dependent variable, whereas we use continuous dependent variables moving forward. So basically, with the sign test, you wouldn't really run this under normal conditions. You would run this if your sample size was very, very small and the sampling distribution was heavily skewed. So if there was a heavily skewed distribution that you couldn't meet the requirements of, say, a t-test, then you can consider running the sign test because it doesn't require normal distributions, right? Or doesn't require large samples. So for this example, we're going to look at the grades.save file. And the hypothesis we're testing, for example, would be grades on exam 2 would be greater than grades on exam 1. Or students that attend class will score better on the exams than students who don't attend class. So once again, this is looking at a before and after situation, right? The same students are taking exam 2 and then they took exam 1 previously. And is there a difference? So the independent variable here is the group, or it's the time, basically, before and after. The dependent variable is going to be basically greater than or less than. So we open up the grades.save file, and we're going to look at students scoring better on quiz 2 than quiz 1. So for example, I did some kind of intervention before quiz 2. Maybe I did an extensive review for quiz 2 because quiz 1 wasn't good. And I want to see if that extensive review before quiz 2 increases quiz 2 scores compared to quiz 1. And that's a very easy hypothesis to test with the sign test. If you don't have the normal distribution or you have an extremely skewed data set, right, with many outliers, then you could use the sign test. Otherwise, if you have a normal distribution that's not heavily skewed and you have a large enough sample, you'd want to use the t-test. The t-test has more power than the sign test. The sign test is what's called a non-parametric test. It's very much underpowered, which is a problem when it comes to testing hypotheses because it leads us to make more type 2 errors. So we're going to open up the grades.save file in SPSS or through a Porto's SPSS, right? It looks like it right here. And we're going to go in and we're going to look at the sign test. So it falls under analyze non-parametric tests. And you're going to go down to legacy dialogues. And we want 2 related samples. So this is very similar to the correlated groups or the paired sample t-test where you have the same individuals in 2 conditions. You're going to check off sign in the middle here. And we're going to look at quiz 1 and quiz 2. So we're going to do quiz 1 first. And then quiz 2, and is there a difference between quiz 1 and quiz 2? Same individuals in both conditions, right? So you could run paired samples t-test or correlated groups t-test, right? But if there's a problem with the sample or a problem with the skewness in the sample, heavily skewed, then we're stuck running the sign test. The sign test does not give us a magnitude of the difference. It only tells us whether there's a difference or there's not a difference. So is there a positive difference? Is there an increase from quiz 2 compared to quiz 1? And that's what we're looking for. So if there's an increase from quiz 2 compared to quiz 1, we call that a plus. Plus meaning increase. If there's a decrease from quiz 1 to quiz 2, we call that a minus. We're not interested in that because we think that quiz 2 will be better than quiz 1 because we've done an intervention after quiz 1. try to make quiz 2 better. So quiz 2 is greater than quiz 1, you get a plus. Quiz 2 is less than quiz 1, you get a minus. We want the pluses, right? If they're equal, we drop. So in the case of a tie, we discard the case, which is another problem with this test because you're just basically throwing away data. So any data that's tied, we discard. We only look for pluses and minuses, and we want to see if we get a lot more pluses than minuses. So the null hypothesis that there is no difference, there should be a relatively equal number of pluses and minuses. For the alternative hypothesis that quiz 2 is greater than quiz 1, we should have a lot more pluses than minuses. How much is going to be dependent on the binomial distribution. So we got quiz 1 here and we got quiz 2. We check off the sign test, we hit OK. And we've discarded all the ties. So what does this tell us? This tells us that quiz 2 was lower than quiz 1 34 times. Quiz 2 was higher than quiz 1 50 times. That's what we're interested in. We're interested in the 50 here because we're hypothesizing that quiz 2 will be better than quiz 1. Right? So if quiz 2 is better than quiz 1, then if you do quiz 2 minus quiz 1, you get a positive change. And that's what we want. The ties get thrown out. Now you can calculate the binomial probability through, the binomial. You can look at a binomial table. You can use a binomial calculator, or we could do something called the normal approximation for the binomial. So that's what you see at the bottom here. This is the normal distribution approximating or used to estimate the binomial. And so we're going to test Z. Just like we test Z all the time for a normal distribution, we have to look at Z. Is Z big enough? Is the Z value big enough to then reject the null hypothesis, where there's no difference between quiz 2 and quiz 1, and support the alternative that quiz 2 is actually better than quiz 1 due to the intervention after quiz 1. And so we look at Z, we get negative 1.637, and the p-value is 0.102. We then compare that to 0.05. This value is not less than 0.05. So we fail to reject the null hypothesis. And if we fail to reject the null hypothesis, we have to conclude that quiz 1 and quiz 2, there's no difference between them. So that intervention that you did at the end of quiz 1 to make quiz 2 better, that intervention did not work. There's no difference between quiz 2 and quiz 1, no significant difference. 0.102 is greater than 0.05. This significance value, this p-value, would have to be less than 0.05 for us to conclude that there is a difference. So in this case, there is no difference between quiz 2 and quiz 1. We fail to reject the null hypothesis. And you can see this skimming through this, right? Fail to reject the null hypothesis. Now, the one condition you need to have to use this normal approximation is that n times p has got to be greater than 5, and n times q has to be greater than 5. Now, p is the probability of success, n is your sample size. So when you multiply 0.5 by n, you have to have a value greater than 5. And the same thing with q. Q is the probability of failure. So 0.5 again, under the null hypothesis, times n. That'd be, in this case, we have a big enough sample that NP and NQ are both greater than 5. That's the only thing you need to have to use to be able to use the normal approximation. Now, this 0.102 is actually a two-tailed test, a non-directional test. If our research hypothesis is that quiz 2 will be greater than quiz 1, right? That's a one-tailed test. We're not looking in the other direction. We're not interested if quiz 1 is greater than quiz 2. We're not interested in that. We're only interested if quiz 2 is greater than quiz 1. So we're doing a one-tailed test. This p-value is a two-tailed test. So we have to divide this in half to get the one-tailed probability. And the one-tailed probability is going to be half of this, which is 0.051, which is still not good enough to reject the null hypothesis. So we'd still fail to reject the null hypothesis, but we're a lot closer if we're doing a one-tailed test. Let's look at another one here. Suppose we think that halfway through the semester, students will adjust to the course. Quiz 3 will be greater than quiz 2. So let's look at that. Is quiz 3 going to be greater than quiz 2? So same thing, analyze non-parametric legacy dialogues, 2 related samples, and is quiz 3 going to be greater than quiz 2? Let's take a look. So quiz 2 and quiz 3 in the same row. Make sure you check off sign. Options, you can put descriptors if you want. You don't need them. I'll leave them blank. Hit OK. So once again, we think that quiz 3, we're hypothesizing that quiz 3 is greater than quiz 2. So it's a one-tailed test. The null hypothesis is that there's no difference between quiz 3 and quiz 2. They're the same. When we do the sign test, we find that quiz 3 is greater than quiz 2 33 times. And that quiz 3 is less than quiz 2 33 times. Quiz 3 is greater than quiz 2 46 times. And we have 26 ties, we discard them. So we're looking at 33 and 46. Is that enough of a difference to say that quiz 3 is actually greater than quiz 2? We can use the normal approximation, the z approximation for this. Now this is a two-tailed z. We have to divide this in half. When we divide this in half, we get 0.0885. And that 0.0885 is not less than 0.05. So we once again fail to reject the null. And if we fail to reject the null, we cannot conclude that quiz 3 is greater than quiz 2. And then let's look at quiz 1 and quiz 5. So we're going to do the same thing, analyze non-parametric legacy dialogues, 2 related samples, quiz 1 and quiz 5. Check off sign. Let's take a look at that. We see that quiz 1 is greater than quiz 5 39 times. We see that quiz 5 is greater than quiz 1 45 times. And we have 21 ties. When I do the normal approximation, I get negative 0.546. And even if we do a one-tail test here, where quiz 5 is greater than quiz 1, if you divide 0.585 in half, we get 0.2925. That's much greater than 0.05. So we once again fail to reject the null. And we conclude that there's no difference between quiz 1 and quiz 5. So whatever we're doing between quizzes to try to raise the scores is not working in all of these scenarios. Now, one reason why it's not working in this data set is we're using the sign test. And like I said, the sign test is severely underpowered. It makes it very hard to correctly reject the null hypothesis with the sign test. The reason why it's underpowered is because it does not take into account the magnitude of the difference, the mean difference that you would see in a t-test. You would see a mean difference. And if we just look at a t-test from this point of view, quiz 1 and quiz 5, let's take a look at the t-test, a paired samples t-test to see if there's a difference. So we're going to do compare means here, paired samples t-test. Is there a difference between quiz 1 and quiz 5? And this is going to look at the means. So the paired samples t-test is going to look at means and standard deviations. And you're going to have much more power with this because you're looking at mean differences rather than plus or minus, right? Because the plus or minus doesn't give you the magnitude of the difference. It only gives you basically a categorical yes or no. There's a difference or there's no difference. So the t-test is much more preferred over the sign test. Don't need effect size for this. Hit OK. Actually, let's put descriptives in here. Looks good. Let's look at the descriptives. So quiz 5 is 7.87. Quiz 1 is 7.47. Is that a statistically significant difference? We see that they're correlated, which is they should be because it's the same person taking both quizzes. And when we go down here to check to see the t-value, we're looking at a one-tailed test, and the one-tailed test here is 0.033, and that is less than 0.05. So if we did this as a t-test, we'd be rejecting a null hypothesis. When we do this as a sign test, we fail to reject the null hypothesis. So once again, if you can do it as a t-test, do it as a t-test, your analysis. Unless you have a heavily skewed distribution, like heavily of many outliers, or you have a really small sample size, there's no reason to use the sign test. The sign test is kind of the last resort situation. And that's it for the sign tests. Hopefully that makes sense. And you followed that. It's pretty easy to do. It's not something we do on a regular basis. We only do it in case of emergency where we have heavily skewed distributions mainly. So that's it for this video, and I'll be back next time with starting to talk about z-tests and t-tests.